So here's section 1.4, mutually exclusive and non-mutually exclusive events. So let's investigate a standard deck of playing cards. Okay, so again, these are all the cards represented in the standard deck of 52 cards. So you see you have hearts, spades, diamonds, and clubs, and numbers from ace all the way to jack, queen, and king. Okay, so I'm going to create here a Venn diagram to represent the event of picking a club or a spade. Okay, so I'm going to draw a Venn diagram. In our sample space, we have 52 cards. And to draw a Venn diagram, I'm going to have to draw some circles here. I'm going to draw one circle that represents my set of spades and another circle that represents my set of clubs. Okay, so I have here spades. Oops, let me just close that. And click on that, delete that. Okay, so I'm going to have my spades and I'm going to have my clubs, and there are 13 spades and there are 13 clubs, and there are 26 other cards on the outside. 13 diamonds, 13 hearts make 26. Okay, and extending from this Venn diagram, well, let's see, find the probability of randomly drawing either a club or a spade from a standard deck of cards. So I'm interested in finding the probability of drawing a club or a spade. So I have to also add the probability of drawing a spade. That's what that or means. We're combining them. Think of like the union of two sets from what we did in our previous lessons. The union of these two sets. I'm going to add the 13 and the 13 and find a probability. So the probability of drawing a club is, well, there's 13 clubs out of a deck of 52, plus probability of drawing a spade, which is 13 spades out of a deck of 52. So 13, again, 13 the number of successful of my outcomes of my event, and 52 are the total number of possible outcomes. Okay, I add these two fractions together. I have 26 over 52, and as in lowest terms, that's 1 over 2, or 50%. Okay, so there's a 50% chance, a 50% probability of drawing a club or a spade from a deck of cards. And so this is an example of two events which are mutually exclusive. Okay, in other words, these are disjoint. So disjoint sets, mutually exclusive. So mutually between the two of them, these are excluding each other, exclusive of each other. Okay. So let's look at another scenario. So create a Venn diagram to represent the event of picking a diamond or a face card. Okay, so our sample space is still going to have 52 cards in there, but this time the Venn diagram is going to look a little bit different. Okay, so I'm going to draw one circle here, and I'm going to draw one circle here. Okay, and I'm going to say this circle here represents my diamond, so D for diamond, and I'm going to say this circle here is my face cards, FC. So now let's just want to highlight something here. So I'm going to highlight what are my diamonds. So I have all my diamonds. Oops, let me undo that for a moment. I'm just going to change the color of that. So let's go back here. Let's see if we can highlight a different color. And let's try and pick yellow. Okay, so let's see. Looks good. Okay, so I'm going to highlight all the diamonds here. Okay, so I've highlighted all those diamonds. And what about the face cards? We have these face cards here, king, queen, and jack. But notice how when I highlighted these things, some of them intersected. So I have the jacks repeating, the jack of diamonds repeating, queen of diamonds repeating, and the king of diamonds repeating. So these sets intersect with these three elements in there. Okay, so in the middle here, I'm going to have the number 3. Okay, because the face cards, jack, diamonds, queen of diamonds, and king of diamonds, are also part of the set of the diamonds cards, because they are diamonds, right? Okay, so how many diamonds cards I have in total? I have 13. So if I already have 3 represented in here in the middle, then I still have to write 10 more in this circle here. And if I have 4, 8, 12 face cards, 3 of them already represented here in the middle, and I have 9 remaining here on this side, so that gives me a total of 12. And if I add up all these numbers, so 10 plus 3 plus 9, and I take away from the 50 deck of 52 cards, then everything outside my set, so I have 30 other cards outside my set. But now let's examine a probability problem using this. So find the probability of randomly drawing either a diamond or a face card. So the probability of drawing a diamond plus the probability of drawing a face card. But because the sets are intersecting, you have to use, think about what happens when you do the formula that you have to account for the intersection of the sets. So you don't want to double count those 3 face cards, so I have to subtract the probability of both getting a diamond and a face card. Okay, so to subtract that probability, because you don't want to be double counting. So remember, you end up double counting those jack, queens, and kings if you include it. So you have to subtract that intersection. Okay, so this equals the 13 out of 52 plus 12 face cards out of 52 minus the 3 jack, queen, and king diamonds that are shared between the 2 sets out of 52. Okay, and then if I add those numbers up, 13 plus 12 minus 3, that's 22 out of 52. And in lowest terms, that is 11 over 26 if I divide the top and bottom by 2, or I can express this as 42%. Okay, and this scenario represents non-mutually exclusive events. Okay, so they're not mutual, meaning there's an intersection between the 2 sets. There's a common elements in both events that we're talking about here. Okay. All right, let's move on. So mutually exclusive or disjoint sets have different attributes and cannot occur at the same time. That's why the Venn diagram had separate circles. So for example, in baseball, a pitch could either be a curveball or a fastball, but not both. Okay, so no intersection. And for mutually exclusive events, if you're interested in just finding the probability of having one event or the other, then you just use this addition principle where you add the probabilities of each event. And there's nothing to subtract. Okay. So here's an example that we can do. Terry is at a fundraiser at which there are 15 days at a spa to be given away as door prizes. Winners are randomly given a spa day from a stock of 2 at the Briars, 4 at Elmwood, and 9 at Wellsprings. She really likes Briars and Elmwood, but hates Wellsprings. Assuming that Terry wins the first door prize, what is the probability that she will get a day at the spa she likes? So the events are B for Briars, E for Elmwood, and the probability that she can either get the Briars or Elmwood is equal to the probability of getting Briars plus the probability of getting Elmwood. Okay, so Briars has a 2 out of 15 chance. 15 comes from the fact, well, that 15 is equal to 2 plus 4 plus 9. So the total number of outcomes is 15, so it's going to be 2 out of 15 plus there are 4 chances for Elmwood, so 4 out of 15, and together when I add those I get 6 out of 15, or lowest terms 2 out of 5 if I divide the top and bottom by 3. And 2 out of 5 is a 40% chance. So therefore, Terry has a 40% chance of getting the spa she likes. Okay, so let's look at now an example of non-mutually exclusive events. Let's just talk about this a little bit more. Non-mutually exclusive events have a common characteristics, which means they can occur simultaneously. So for example, rolling an 8 or doubles using 2 dice. I mean, so rolling 8, you can get doubles at the same time. So 4 and 4 is a double, and that gives you 8. So when you have this scenario, when you have events that have common outcomes that can occur simultaneously, then that is a non-mutually exclusive event. And for that, we have to use a formula that's slightly different. So having a probability of A or B, this is the probability of A plus the probability of B minus those common elements of the probability of having A and B happening at the same time. So let's just go through a couple of examples here. So in electronics manufacturer is testing a new product to see whether it requires a surge protector. The tests show that the voltage spike has a 20% or 0.2 probability of damaging the product's power supply, a 60% or 0.6 probability of damaging the downstream components, and a 0.1 probability of damaging both. Okay, so there's probably 10% missing somewhere else, somewhere along, but so we're just still going to just use these numbers. So determine the probability that a voltage spike will damage the product. So the event is, let's define the event. So A will be referring to the power supply, so damaging the power supply. B will refer to damaging the components. Okay, so the probability of A happening is 0.2. Probability of B happening is 0.6. The probability of both is equal to 0.1. Okay, and the tests for that missing percentage, well, that would probably mean the tests don't damage the product at all. Okay, so I'm interested in what is the probability that the voltage spike will damage the product. So either damaging the power supply or damaging the components. So I'm going to say the probability of damaging the power supply or damaging the components. And instead of saying A or B, you can also use my notation, A union B, because that's what that means as well. Okay. And so I'm going to say the probability of event A plus the probability of event B minus the probability of A and B. Again, in my special notation, you could say probability of A plus the probability of B minus the probability of the intersect. So that's this sign here, intersect of A and B. Okay, and if I plug in my numbers, I get 0.2 plus 0.6 minus the probability of damaging both, which is 0.1, and that's equal to 0.7, or 70%. Okay. So my concluding statement here would be, therefore, a voltage spike has a 70% chance of damaging the product, which means maybe if you're a manufacturer, you would probably want to invest in a surge protector for this product. Yeah. Okay, example number 3. 2 fair dice are rolled. What is the probability of rolling a sum less than 6 or rolling doubles? So the first event, A, will define as a sum that's less than 6. And my second event, B, will be the probability of rolling doubles. Okay, so let's look at the first one, probability of A. And to know this, you probably have to go back to your notes a little bit when we had the table when you rolled 2 dice, and you have to look at the number of ways you can roll a sum that's less than 6. And if you examine that table, perhaps I can find it here. So let's just look at, I believe it was theoretical probability. So let's just look at this. Yep, here it is. So how many outcomes are there to roll a probability of less than 6? You have here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So all of these possible ways to roll a number less than 6. So it's 10 out of 36. So there's 36 possible outcomes. When you count all the outcomes in this table, there's 36 possible outcomes of rolling a 36, rolling 2 dice. So there you go, 10 out of 36. Now the probability of rolling doubles, how many ways are there to roll doubles. Well, there's 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So there's 6 ways to roll a double. So 6 out of 36. Okay, and the probability of doing both. So I'm going to make so probability of both happening here is equal to. So let's look again at our table. Rolling doubles and rolling less than 5. So you can go 1 1, that's a double, and 2 2, that's a double. But and 2 2 would either give me 4, would give me a 4 and give me a 2 here, but I can't do 3 3. So 3 3 would give me a 6, which is greater than 5. There's only 2 possible outcomes, this one here and this one here. So I'm going to just write here 2 out of 36. So my formula, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both A and B. Okay, so that's going to equal 10 out of 36 plus 6 out of 36 minus 2 out of 36, which is 14 out of 36. In lowest terms, I could say 7 out of 18 if I divide the top and bottom by 2. And 7 out of 18 is 39%. So I'm going to say here there is a 39% probability of rolling doubles or a sum less than 6. So just a note at the end here, when calculating probability of one event happening or another, it is important to carefully count the outcomes. And this is relatively easy to do when the events are mutually exclusive, so when there's nothing in common between the two sets, but often more challenging when the events are non-mutually exclusive. You got to really read the questions carefully, make sure that the events that they're giving you do not have common elements that intersect. If they do, then you have to use the formula for non-mutually exclusive events.